All right, let's dive right into this explainer. I want you to think for a second about the sheer invisible power it takes to literally tear through cellular architecture and fundamentally alter your biology. It's a pretty staggering concept, right? Well, today we are going to completely unpack the somatic effects of radiation. This is a topic that demands a really deep exploration because it bridges the raw, unforgiving physics of energy transfer with the incredibly intricate machinery of the human body. We're going to move step by step from the underlying mechanical realities of exposure right through to the specific clinical effects and real-world medical examples.
Now, when we talk about radiation, it often sounds, well, incredibly abstract. We hear words like waves, particles, energy fields, but we really need to ground ourselves with a core question here. What actually happens to our bodies? What is physically going on with the cells, the organelles, and the DNA inside of us when exposure occurs? You see, we can't just think of this as some mysterious, invisible force. We have to look closely at the microscopic cellular reality of human tissue under direct bombardment.
To give us a complete picture, here's our roadmap for today. 1. Introduction to radiation effects. 2. Defining somatic cells. 3. Types of somatic effects. 4. Real-world effects examples. And finally, 5. Why this matters today. Okay, kicking things off with Section 1, Introduction to Radiation Effects. Let's establish exactly how this invisible energy interacts with biological matter.
So here is the absolutely crucial point. Radiation isn't just passive energy passing harmlessly through us. Not at all. It transfers that energy directly into our tissue, causing some profound mechanical and chemical disruptions. At the microscopic level, we're talking about intense ionization. Basically, radiation actively strips electrons right away from stable atoms, creating free radicals and highly reactive oxygen species. And those reactive ions, they trigger a highly destructive chemical cascade inside the cell. This isn't just a gentle bump. It can lead to direct, localized, double-strand breaks in your DNA, fundamentally compromising the biological blueprint of your tissue.
Moving on to Section 2, Defining Somatic Cells. Before we can really get into the consequences of those cellular collisions, we have to define exactly what part of the body we're talking about. Somatic cells make up the vast, and I mean vast, majority of your biological structure. We're talking about your skin cells, your organ tissues, your muscles, your bones, the neurons in your brain, literally everything that constructs the physical framework of you. The only things explicitly excluded here are the reproductive genetic cells, like sperm and egg cells. Actually, fun fact for you, the word soma comes straight from the Greek word for body, so it makes perfect anatomical sense.
This distinction perfectly illustrates the strict boundary of our topic today. When we contrast somatic effects with genetic effects, it's a total game changer for understanding radiation biology. Somatic effects impact only the exposed individual. So, if a somatic cell is mutated or destroyed by radiation, it leads to localized tissue damage or malignancies, like cancer, solely within that one host organism. Genetic effects, on the other hand, happen in those reproductive cells we just excluded. Those are the germline mutations that get passed down to alter future generations. But for this explainer, we are keeping our focus strictly on the somatic side, the individual experiencing the direct exposure.
All right, with that definition locked in, let's jump into Section 3, Types of Somatic Effects, where we look at early versus late manifestations.
Scientists systematically divide somatic effects into two distinct types based on when they actually show up clinically, and the cellular logic behind this is fascinating. First, we have early or acute somatic effects. These show up really quickly. We're talking within days or weeks. Why? Because acute effects typically happen in rapidly dividing cell populations, like the skin or the lining of your gut, where cellular damage brings tissue regeneration to an almost immediate halt. Then, secondly, we have late or delayed somatic effects. Now, these are much sneakier. They stem from complex, slow-brewing mutations that don't actually kill the cell right away. Instead, they subtly alter its replication code, taking years or even decades to finally show up as a malignancy.
Let's look at how this actually builds across the biological timeline. Regardless of whether the effect is early or late, the biological progression always follows these exact sequential steps. Step 1. The initial radiation exposure happens. Step 2. That exposure causes the localized cellular damage we just discussed, like those DNA double-strand breaks. But here's the really critical part. Why does it actually become a physical symptom? Well, it happens because the damage successfully bypasses your body's cellular repair mechanisms. The cell fails to undergo apoptosis, which is just a fancy scientific term for programmed cell death, and instead it survives. It propagates the error until we hit step 3, where the microscopic damage cascades enough to manifest as a real macro-level physical symptom.
Let's zoom in even closer for Section 4, real-world effect examples, looking directly at medical conditions.
So a rapid, acute dose of radiation impacting those rapidly dividing cells we mentioned causes immediate issues within days or weeks. A classic somatic example of this is skin erythema. Think of it as a severe, localized radiation burn on the skin. On the flip side, long-term chronic exposure over a lifetime, or perhaps surviving a really massive acute dose in the past, is linked to delayed somatic problems decades later. A prime example here is the formation of cataracts in the lenses of the eyes, as damaged proteins just slowly aggregate over time. It's wild to think that the exact same hazard creates vastly different symptoms depending entirely on the timeline of the exposure.
Tying right back into those acute reactions, we absolutely have to talk about the threshold dose. This is a crucial concept for what we call non-stochastic or deterministic effects. Basically, for many acute somatic injuries, there's a specific, measurable amount of radiation that must be absorbed. Below that specific threshold, your body's natural cellular repair mechanisms can fully handle and fix the DNA damage. The probability of the injury is essentially zero. But the second that threshold dose is crossed, the probability of that acute somatic effect occurring jumps straight to 100%. It's an absolute biological tipping point where your body's defenses are suddenly and completely overwhelmed.
Finally, let's wrap up with Section 5, why this matters today. We really need to connect all this dense cellular biology back to our everyday world. There's a guiding principle in this field that perfectly hits the nail on the head. A full understanding of somatic effects is the foundation of all modern radioprotection. Mapping out all these deep somatic details isn't just some academic exercise for molecular biologists, It is the rock-solid foundation for how we design medical safety protocols and protect workers all over the globe. Every single time you get a dental x-ray and they place that heavy lead apron over your chest, or every time a nuclear medicine technician gears up for their shift, those strict regulations are built entirely on our calculated understanding of threshold doses and how our somatic cells react to ionizing tracks of radiation. And that brings us to the end of our detailed exploration today. But before you go, I want to leave you with one final thought to ponder. As medical technology continues to advance, and we gain the incredible ability to track the intricate somatic effects of radiation down to individual proteins and single DNA strands, how will these new discoveries revolutionize the safety standards we rely on every single day? The science of radioprotection is never truly settled. The deeper we understand the beautiful, fragile complexity of the cells forming our bodies, the better equipped we are to protect them. Thanks for joining me on this explainer, and I'll catch you next time.